of helping you with it. It's going to be at best decent. And we only have an hour, so we don't want to spend all of our time on Lagrange. There's a lot of other questions here. So let's just take this first one. Okay. So if we're going to use the first three terms of the Maclaurin series to approximate that function, what's our maximum error? Well, according to the Lagrange, it's the next derivative times, or the next derivative evaluated at C. And this is what's complicated. What, you have a lot of background noise in your...
Yeah.
Okay.
Here, give me a minute.
What's that?
Yeah.
Yeah, there.
I can hear you.
Much better. It's hard for me to think when I hear all that background noise.
David, I say hi. David doesn't want to hear it. Yeah. Don't.
So what she's basically done is says she's calculated the third derivative. Which is
Okay.
1/8 e to the x over 2. Now, why she has a 0 there, I'm not sure. I think she means x.
Where?
Right here in number 1.
0.1. She's taking that from the interval, I think.
The interval is 0.1 to 1, or negative 0.1 to 1. But nonetheless, let's not spend all of our time trying to figure that out. 3 factorial comes from the n plus 1. So the first 3 terms of this Maclaurin series only go up to the second derivative. And so that's why this is f third derivative. Now, the number she plugs in here, 0.1 to the 3. That's an end point of that interval. And what we know about these intervals is that we get further and further away from 0, they are less and less accurate at predicting e to the x over 2. So the way you come up with the c is the maximum, or we could have used the minimum value, it wouldn't have mattered. In other words, we could have used negative 0.1 here just as well as positive 0.1.
Okay.
Maybe she did put in 0 for x there for that reason. Because this is supposed to be 1/8 e to the x over 2. All right, she must be. Still not sure I totally understand that. But notice that whether we use minus 0.1 or plus 0.1, it's not going to matter because we're going to cube it, but then the absolute value is the key. So when you take the absolute value of that, you get this number here. And that's the maximum error of that approximation. Given that the maximum error is going to occur at one of these endpoints. Number 2. What's the easiest way to do number 2?
Just plug it into the series for E.
Right, exactly. In other words, we know the series for E. Here, let me bring up my list of convergent tests for divergence. Oh no, that's not what I want. I want the series one. You have all those memorized. E is what? It's x plus x squared plus x, or x squared over 2 factorial plus x cubed. Here,
Yeah.
let me find all of those series because they're important. Those power series, I think that it's further back. But anyway, it's not key that we know that, or that I know that, as long as you know it. So we're plugging in minus 2x squared for x in the power series. Okay, and that gives us this power series, which we can put an nth term on. You see how we get this nth term? In other words, we do need to figure out that nth term.
Yeah.
Okay. And usually this is a little bit of an art, figuring out the nth term given the first 4 terms of the series. But we can see that when n is 0, we're going to get 1. When n is 1, we're going to get this term. When n is 2, we're going to get this term. Notice that there's a 2 factorial under here to begin with, but it becomes 4 over 2 factorial, which makes that coefficient 2. And this is a 3 that began with a 3 factorial and whatever numerator. Let's see, n would have been 1, 2, 3. So we would have minus 8 over 3 factorial, which is 6. That's minus 8/6. That's where that minus 4/3 come from.
Okay.
Okay. And then if you were to play around with an nth term, and that's pretty much what you have to do, is just kind of play around with it and make sure this nth term gives you these first 4 terms. Okay. Now we're talking about the interval of convergence. And there's actually 2 terms that don't really mean the same thing. And one of them is the interval of convergence, and the other thing is the interval of convergence. So, and then I'll explain why they don't mean the same thing. The convergence interval, let's call it. And you use the ratio test on most of these. Since we have the nth term right here, then we want to know what the interval of convergence, or the convergence interval, is. And that's almost always the ratio test. Remember, the ratio tests divides a to the n plus 1 divided by a to the n. Here, let me bring up my drawing tablet here. In other words, the ratio test is the limit of a to the n plus 1 over a to the n as n goes to infinity. And we're looking to see whether that ratio comes out to be less than 1, greater than 1, or equal to 1. Well, you can see that that's what she's done. Oops, hold on. I got a bigger monitor. That's one thing I did do yesterday, and it actually is Okay. There is the a to the n plus 1. Do you have any questions at all about how to get that?
No, I get that pretty well.
Well, when you divide by a to the n, it's the same as multiplying by the reciprocal of a to the n. Well, here's the reciprocal of a to the n. Okay? Now, we talked about this last time, but there's a lot of tricks you can use when factorial is involved and when exponents are involved that differ by only 1. In other words, if I have this expression to the n plus 1 divided by that same expression to the n, I can subtract exponents and I get just minus 2x squared in the numerator, which is what that is there. You see that? In other words,
Yeah.
when you're dividing same base, you subtract the exponents. And that's all we do there. That's to the exponent 1. And in factorials, we talked a lot about this. We have n factorial over n plus 1 factorial. Well, that's equal to n plus 1. And if you don't understand that, just try a few numbers. Try 6 factorial over 7 factorial. You get 7 in the denominator. Try 11 factorial over 12 factorial. You get 12 in the denominator. Okay? So the limit of this expression as n goes to infinity is what?
0, right?
Yeah. Even though there's a variable in the numerator, it doesn't matter. As long as the denominator is going to infinity for any given variable for x, this thing goes to 0. Now, if there was an n in the numerator, that wouldn't be true. But as long as the n is in the denominator and it blows up, then the whole thing goes to 0, which is less than 1, which means it converges for all real numbers, meaning no matter what x is, I could make x a billion, and the denominator is still going to eventually outpace it and drive that whole limit to 0. So that means it converges for all real numbers because it's convergent no matter what x is. Now, the next part of that. Let g be a function given by the sum of the first 4 non-term 0 terms of the power series for f of x, okay. The error that we're going to get by using just the first 4 non-terms of that power series is going to be the first 4 terms minus the entire thing, and that'll be our error that we're going to incur by using only the first 4 terms of this thing. And if we can show that that's less than 0.02 on that interval, that error is that, which is, she says, alternating series error here. Because we're still talking about the same function. In other words, we're talking about this function. Here's the first 4 non-zero terms. Well, notice what the next derivative is. In other words, that was f prime, f double prime, f triple prime, f quadruple prime is going to give us a 16 in the numerator, right?
Yep.
A 4 factorial in the denominator. And we're going to use the right or left-hand endpoint of this interval as our C. And it's to the 8th power, because that's the very next term would be x to the 8th power. And so we can come up with that number, and it's equal to 0.0112, which is less than 0.02. So by using the Lagrange error, we've proven it.
Alrighty.
Stuff is tough, especially this Lagrange. You are actually the first person I have ever gone through the Lagrange formula with. Even my other two Calc BC students did not do the Lagrange remainder.
Wow.
And that is because it's not on the Calc BC test, the AP test.
Really? Why is she teaching it then?
Well, for the same reason they teach all kinds of things in geometry that you never get asked again on any tests. They always go a bit above and beyond. So, and that's why I've never worked with anybody else on it, because nobody else, they've either taught it or they've been told that it's not going to be on the AP test, and so don't worry too much about it. All right, number 3. Unfortunately, it doesn't help you with the test you're going to take today. You need to know this.
Oh, no.
But it might be a little helpful to you to realize what the meat of this stuff you're going to have to remember is. And the ratio test is a big one. That is on the BC test. So let's see, write the 3rd degree Taylor polynomial for x.
I get this one pretty well. We can just skip it.
Yeah, I was going to say, this is fairly straightforward. Well, and then use it to approximate 1.5. Well, of course, the way I'm going to do that is to substitute 1.5 in for x, which is what she's indicated here. Okay, now she wants to look at the 4th derivative, whose absolute value is less than or equal to 3 for all x in that interval. Use the Lagrange error bound on this. And the error bound, of course, is the full function minus the first 3 terms of the Taylor polynomial. That's how you get the error. That's an absolute value sign, not a 1. And that has to be less than the 4th derivative evaluated at some z times 1.5 minus 2, that's x minus a, all over 4 factorial. And then what she has used here, I guess she's just reduced this. Yeah, you get.
Did she use alternating error or alternating series error bound?
Yeah, where'd she get that? That's not in my book. She introduced that on her own? In my book on Lagrange and the remainder, it doesn't talk about alternating series.
Oh, well, she told us that you just take the next derivative, so the 4th here, I think, and then plug in the x minus a.
Well, that's regular. Yeah, I mean, that's regular. I don't see where that's special to alternating series. So I'm not sure exactly what's going on there. But she simplifies this. Now, where did she get the f to the 4th of z being equal to 3? Ah, right here. She knows that if the 4th derivative evaluated at x is less than 3, then she can use that as the f to the fourth derivative of z. In other words, whenever you're working with these things, you always want to use the maximum error. Well, we know from this statement here that the maximum error is less than 3. So she can use 3 instead of f to the fourth derivative of x. In other words, instead of f to the fourth of z, z is some point between c and x, or between x and a, rather. That's what z is. And essentially what z is the worst case scenario. In other words, whatever produces the maximum error, that's the z we're going to use. There's an example in the book that works with sine as the function, and you know that the most sine can ever be is 1, the least it can ever be is -1. So when you're doing something like this, you can plug in 1 or -1 to proceed. And so she gets this number here. Explain why f of 1.5 is not equal to -5. Well, let's see. She's plugged in other words, I guess she's assumed that it's equal to 5 and determined that the error would be 0.042, which is greater than 0.0078, which is what we got. And that is in that interval. So that can't be a true statement. There's no way f of 1.5 can be equal to -5, because if it was, notice that 1.5 is in our interval. So f of 1.5 should give us an answer that is less than this error. But it doesn't. When we actually plug it in, we get 0.042 is greater than that. So that cannot be equal to -5. And maybe this is...
I got a 0.0078 for that.
Well, 0.0078 was the Lagrange error bound. But if we assumed that x of 1.5 was -5, in other words, we can always say that the error of any approximation is the complete series minus g of x, which is the Taylor polynomial. In other words, if you want to solve for your error, that's how you do it. You take the infinite series, you subtract the part of the Taylor polynomial that you're going to use to approximate it, then that's your error. Well, when she did that here, she came up with 0.042, which is correct. But that's greater than the error that we're supposed to be getting. Also apologize, I got either a bad cold or bad allergies.
No problem.
I have some tea here that should hopefully help my cough.
Also, David, I'm sorry, I realized I only have half an hour, though, unfortunately. So I got about 3 minutes left here before I have to go.
All right. Is there anything you want to look at in those 3 minutes?
Yeah, could we do number 9 or number 14 quickly?
Yeah. Whenever you see a sum like this that has a factorial and an exponent to the n, think ratio test. And the reason being is the ratio test works so well because we get to cancel out the factorials and the exponents. Notice again, we have 2n plus 2 factorial all over 2n factorial. Well, we know what that is. That's if you plug in some numbers, you'll figure out that that's 2n plus 2. And we have...
I had trouble simplifying that. I got all the 2n plus 2 to the factorial. I did all the n plus 1.
Well, 3 to the n over 3 to the n plus 1 is 3 in the denominator.
Okay, yeah, I see that.
As long as you're left with just n's in the numerator and n's going to infinity, then that limit is infinity, which is greater than 1. So that's a divergent series because the ratio test has it greater than 1. Now, as far as simplifying this, it actually looks like 2n plus 2 factorial over 2n factorial must be equal to that numerator. And you could prove that. If you ever have problems with this, we have 2n plus 2 factorial divided by 2n factorial. Well, let's stick in an n of 3. If we put an n of 3 here, we have 8 factorial divided by 6 factorial. That's 8 times 7. Well, the 2n plus 2 is 8. Remember that was n was 3. And the 7 is 2n plus 1. So this simplification of that simplifies to 2n plus 2 times 2n plus 1. And how you would figure that out really is almost a trial and error. You get kind of used to doing it after a while. But the best way I do it is plug in numbers. Just pick some numbers for n, see what you get, and see if you can figure out how to write 8 times 7 as a function of n. Remember, our n that we picked was 3. So 8 is 2n plus 2, 7 is 2n plus 1.
All right, I think I see. Thanks, David.
You're welcome. Have a good day. Good luck on your test.
Thank you. You too.
Bye-bye.